All right, it is time for the version J AP Physics C Electricity and Magnetism questions from 2025. This is my first time seeing them. They just released. I just got I just saw them online on AP Central. So, yeah, let's go ahead and take a look. You'll get my first reactions and my first solutions to this. So, question one. You have an isolated air-filled capacitor. It's basically a cylindrical capacitor. And both of the radii are much smaller than the length, so basically we can treat this as an infinitely long cylinder and ignore edge effects. Equal absolute value of charges, which makes sense. And you have to, okay, derive the electric field in between the capacitors. That's easy. All right, looks like they're finally giving us some calculus. Let's go ahead and take it. So it says using Gauss's law, we have to start this with Gauss's law. Let's just go ahead and write that down. Right, via Gauss's law, we do actually get to change this. Notice that you can't have length in your final answer, but you can use length to help you get the final answer. Basically, you're going to create a Gaussian cylinder of radius lowercase r and the same length as the cylinder, or whatever length you want, actually. Make it as big or as small as you want, because edge effects don't matter here. The enclosed charge should be given by the charge. Let's see, this is a conductor, I believe. Yeah, two conducting. So that means that all of the charge on the inner cylinder is on the surface. And the surface area of your inner conductor is 2 pi r1l, where these two l's are going to be the same thing. Again, you see that it doesn't matter because they're going to cancel out. That implies that your electric field is going to be given by sigma r1 over r epsilon naught. That is exactly what I expected it to be. And this should all be sigma 1, by the way. Yeah, that's very easy, actually. You just create a Gaussian cylinder, length will cancel out. All of the charge is on the area of the inner cylinder, and there you go. Derive an expression for the absolute value of potential difference. That's also easy because you can say that the potential difference is negative integral of the electric field from R2 to R1. We're doing R2 to R1 because you're going from lower potential to higher potential. This will actually make my potential difference positive of the electric field with respect to R then. So that's going to give us negative integral from R2 to R1 of sigma 1 R1 over R epsilon naught dr. And that's going to give you negative sigma 1 R1 over epsilon naught natural log of R, which will just give us, let's see, R natural log of R1 minus natural log of R2, so R1 over R2. But notice that R1 is less than R2, so that natural log is going to be negative. That's equivalent to us saying sigma 1 R1 over epsilon naught ln of R2 over R1, which is now positive. So I'm making use of the fact that you can take this negative sign. Natural log of x to some power is equivalent to n, or that power rather, natural log of x. So I'm just flipping the inside. I'm taking it to the negative 1 power and getting rid of that negative sign on the outside. There you go. All right. Sketch a graph of the electric field. And let's see, R2 is the outer shell's radius and R1 is the inner shell's radius. So, okay. And R1 and R2, and the two magnitudes of charges are equal. So that's actually a very easy electric field graph. It's 0 until you get to R1 because conductor. Your enclosed charge is going to be 0. It'll jump up and have a 1 over r relation until you get to R2, in which case, if you use Gauss's law, your enclosed charge jumps back down to 0. And therefore, no electric field via symmetry and Gauss's law again. Super easy. All right, derive an expression for the capacitance if you insert a dielectric. My goodness, this is easy. Wow. Okay, I swear, it's not even been 5 minutes, and I'm almost done with the first question now. Capacitance, I'm not even going to bother erasing this stuff. Capacitance is equal to charge over voltage. We found voltage in the previous case. Note that with the dielectric constant, basically all that happens is you change all of your epsilon naughts to kappa epsilon naughts. That's all a dielectric does. So it's going to increase the capacitance basically just by a factor of kappa from what you would have had if you just left it filled by vacuum, essentially. So let's solve for capacitance with a vacuum, and then we'll just put kappa in there. So charge on one of your charge on one of your cylinders, let's say the inner one, because that would be positive charge, is going to be given by sigma 1 multiplied by the surface area of your inner conductor, which is 2 pi R1L. And then you divide it by voltage. So that's going to be sigma 1 R1 over epsilon naught, natural log of R2 over R1. Wow, okay. Okay, this is super nice. Okay, so 2 pi L epsilon naught over natural log of R2 over R1. I don't really care to try to simplify that down anymore. I don't think I'm going to be able to. So that tells us that the capacitance, I'm running out of room here, is going to be 2 pi L kappa epsilon naught natural log of R2 over R1. Again, all of your epsilon naughts just change to kappa epsilon naught because that's all the dielectric constant does. There you go. We're done with question one. I don't even know how long that took. Let's go ahead and move on to question two, though. Ooh, finally, magnetism. This is definitely going to have a little bit of calculus in it. I can already tell that because it looks like the first question asks about induced voltage, and you're given a flux that varies with time, which means Faraday's law, and Faraday's law has a derivative. Okay, let's actually read the question, though, and then we'll go ahead and get started. So you've got a you've got a rotating thing. Magnetic field is in the negative z direction. I'm kind of bored already reading it. There's a constant angular speed and a period, and there's your flux. Okay. Let's see what I can do without actually reading the rest of that. All right. The absolute value of the induced voltage is E. Partially completed bar chart tells. Oh, okay. This might not be quite as nice as I thought it was going to be. Okay. Draw bars to represent. Okay, so we actually have to find the induced voltage. Let's go ahead and do that. So that's going to be given by the uh, magnitude of the derivative of flux, and we're already told flux is BA cosine of omega t, which means that you're just going to get uh, omega BA sine of omega t, just like that. So omega BA sine of omega t. Notice that we are plotting the absolute value, so we're going to keep it like that. All right. So at time t is equal to 0, you should have a 0 induced voltage then, according to our function that we just did. So let's go ahead and write 0 according to what it says we need to do. So go ahead and write 0 there. All right. So let's see. So relative to E shown at 3/4 t. So at 3/4 t, 3/4 of your period, you've got this much, which means that okay, let me just draw a graph of what sine as a function of t looks like, as what this should look like. So you're going to start with 0, and basically what 3/4 t is going to look like, that's going to be this spot right here, which means that 1/4 t should actually just have the same magnitude of voltage, and then half t should have 0. There we go. So I'm just kind of making use of what a sine graph looks like to help me visualize this a little bit better. This is a fourth t, this is 3/4 t, t, and half a t, and then 0. So pretty easy. Okay. Yeah, you didn't really actually need much calculus there. Okay. Derive an expression for the maximum induced current of the loop. Begin your derivation. Okay, we're already partially done, so I'm just going to say refer to my work in part A because I already did a little bit of that derivation. So maximum induced current in terms of stuff, well, we can just say see above because we already found voltage. And then we can say that I is equal to E over R. So that should give us omega BA over R sine of omega t. And again, these are all absolute values. So that's going to imply that I max, well, sine can go to 1. So it's omega BA over R. Not too bad. So we already found voltage. We can just divide by resistance via Ohm's law to help us get current then. Sketch a graph for the instantaneous power dissipated. Okay, not too bad. Because we can say that power, I'm just going to write this equation off to the side, power is equal to I squared R. We already found I, so that's going to give us omega squared B squared A squared R sine of omega T. I'm going to erase all of this stuff here. All right. And now we have to plot that power as a function of time. It doesn't look like we have to label anything, which is fine. All right. So sine squared should be sine squared, not just sine, sorry. So it should look something like this. Oh, geez, that's bad. Sorry, again, I'm bad at drawing on my tablet, but it should be a sine squared function and looks something like this. Okay, that's probably about as best as I can draw. It should be proportional to sine squared of omega t, and your maximum value for power should just be everything out front here. So, yeah. Indicate why your sketch is consistent. Briefly justify your answer. Yes, it is consistent. It is because power is equal to I squared over R, which via Ohm's law is equal to E squared over R. So power is zero when uh, voltage is zero, and power is maximal when the absolute value of voltage is maximal as well. Very easy. Okay. A little bit disappointed. I wish we had like a railgun question or something like that. So, all right, experimental design. I looks like it's similar to the physics 2 one almost. Let's just go ahead and clear everything. Okay. You're asked to determine the resistivity. You have a voltmeter, ammeter, and ruler. This is easy. I'm not even going to attempt to write the thing down for the procedure, but let me still show you the formula that I want to use. To find resistivity, you have to make use of R is equal to resistivity, length over area. So resistivity is equal to R A over L. But then to find resistance, you need to use the voltmeter and ammeter. R is equal to delta V over I. So that implies that resistivity will be delta V A over I times L. Now, this is a variable power supply and it is a uniform resistivity, which means that we can measure the radius of our resistor with a ruler to find area using pi r squared, right? Pi times radius squared. Measure the length of your resistor using your ruler. Vary the voltages. Measure the voltage across your resistor. You put a voltmeter right here. Measure the current across your resistor. Put an ammeter right there in series with the resistor. Vary the voltages in multiple trials, right? Boom, you're done. So you can measure current here, voltage, and then length and area using your ruler. That's it. Okay. How should you create a graph then? That's also pretty easy. All you have to do is just create a graph of voltage and current, and then you'll get a straight line, and that slope of that line, according to our equation, will give you resistivity length over area, which implies that resistivity is going to equal slope times pi radius squared or area divided by length. There you go. Super easy. All right. You are asked to use a graph to determine resistivity of things with different lengths, and you're given the area. Are you kidding me? Why are these so easy? Um, okay, I mean, again, like I said yesterday, it's nice because that means I don't have to spend 4 hours on these, and instead I can just do like half an hour and, get on with the rest of my life. But, um, yeah, this is, I don't know, I feel like it's a little bit too easy. So R is equal to rho, L over A. That implies that this is already going to be linear if you just plot, R and L. Yeah, how do you graph it then? Well, super easy. Same as like I said in the previous video, you do have to scale your axes. I believe that you guys can plot data that you're already given. You just do R in ohms, you do L in whatever units it gives to you, meters. 0.05 and 4 are the endpoints then. So 0.05 and 4. Right, you're gonna get some straight line. Um, Again, fill half the graph. Um, yeah, it's guys, it's tedious. I don't want to actually do this on here. Plot your data points, get a straight line, take 2 points on the line just like you did in my mechanics video, and you're gonna find that the slope is equal to R over L, which according to our equation, which I so happen to delete, so let me go ahead and rewrite it. R is equal to rho 2 L over A. Your slope is going to equal the resistivity over area. You are given the area as a constant, which means that resistivity is equal to A times slope. Um, yeah, if you want to say what you got for the slope using this data, go ahead and drop it in the comments and I can, tell you whether you got a reasonable value or not, but I don't really want to try to graph that right here. It's kind of tedious. So what I wish that they did, because they used to do this, is I wish that they gave some like bolder lines for these, because like right now it's like you have to actually count your grid spaces and everything. And it's just kind of annoying. Like right now everything's the same uniform thickness out of all of these lines. Like nobody wants to count how many lines you have and create a reasonable scaling for that. So, okay. Anyway, all right. Two long wires. This seems like it's another magnetism question. Two long parallel wires are a distance of 2D apart. They both carry current I's going in opposite directions. And oh wow, okay, you have two spheres. This one, like with the mechanics one, it seems like this one's gonna be hardest. So I'm gonna try not to let my brain shut down right now. Yeah, okay, and they both have positive charge and they're both moving in the plus x direction. So F1 is the magnitude of the magnetic force on sphere 1, and F2 is the magnetic force on sphere 2 due to both currents, and we have to figure out their forces. Okay, this is actually easy. So you have to use right-hand rule to determine the direction of fields first at both points due to both currents. So due to wire S, you are going to have a field pointing out of the page on sphere 1. So I'm going to call that B subscript of S. And then due to wire 2, you will have a magnetic, or wire T, you will have a field pointing into the page. Meanwhile, at sphere 2, you're going to have pointing in from sphere S and pointing in from sphere, not sphere S, wire S and wire T. So they're both going to be pointing in, which means you are going to have a stronger magnetic field at that point. Now, magnetic force, I'm just going to write this off to the side. It won't be part of my justification, is going to be QVB, and I would put the sign there, but all of your angles are 90 degrees here, so that's not too bad. Right. So based on right-hand rule, that implies that the total force on sphere 2 is going to be upwards, whereas the force on sphere 1 is going to have a downward component due to this field and an upward component due to the second field, the BT. But those two forces are going to cancel, whereas for sphere 2, they're going to add together. Justify my answer for sphere 2, the two fields, the magnetic field is stronger. I'm just going to write that. Field is stronger due to right-hand rule, RHR slash Biot-Savart law. So Lorentz force law says that's the QVB. Lorentz force law says bigger force if Q and V are the same, which they are. Okay, pretty easy. We're probably going to have to derive that. Derive, why just field? Why not do force? Force is not hard to derive. Okay. Derive an expression for the total magnetic field. This is easy. You just have to use Ampere's law for this. It's an infinitely long wire, so integral of B dot dl equals mu naught times I enclosed. So the magnetic field due to sphere S is going to be given by or multiplied by, we'll say 2 pi r. I'm going to create an Amperian circle of distance d, actually, not r, d, around wire s, and that should just equal mu naught times I. That implies that the magnetic field due to wire s is mu naught I over 2 pi d. Do the same thing with wire T. It's literally going to give you the same thing because it's the same enclosed current and same distance away. And like we said, the total magnetic field is just equal to the sum of both of those then. So you're going to get mu naught I over pi d. Yeah, there you go. And later, okay, one more thing and then that's the end. All right, Brett, this was quicker than the mechanics exam. Oh my goodness. Okay. Later, wire 3, you get a 3i and you have sphere 2. Indicate whether that is going to be a greater oh, is it going to be greater or less than? So in this case, your magnetic fields are actually going to partially cancel. You're going to end up with mu naught I, 3i over 2 pi d due to wire t minus for the magnitude of the new magnetic field, that is. So wire t's minus wire 1. Right, it gives you the same thing. It's the same field. It's the same field, but is it in the same direction? I don't think it matters because it's just magnitude of force. Yeah, they're the same. It's the same. Because you have the same magnitude of total field, same charge, and same velocity. Therefore, same force. All right. How long did that take? I don't know. Thanks for watching, guys. Uh, yeah. I don't know. Hopefully, if you took my class over, hopefully I over prepared you for this instead of under prepared. Um, yeah, that's. I don't really know what to say. I don't. Yeah. Again, I'm glad that it didn't take too long, I guess. So, thanks for watching, guys. I'll create a physics 1 video tomorrow for their FRQs.